to another of It's Not Quantum Physics. Today we are going to talk about electrical power. Okay, so we're going to start with a quick recap of the electrical energy equation. In this case, I would like you to use the E equals V times I times T, remembering that E is energy, V is potential difference, I is the current, and T is the time, and remember time is always in seconds, to answer the following two questions. So I'd quite like you to pause the YouTube video here, have a go at both of those questions, write down your full workings, come up with an answer, and then carry on with the YouTube and we'll go through the answer together. Okay, well done for having a go. So let's now have a go at these answers together. So question one, we need to write down what we know. So we want to work out the energy. We don't know that. We do know that the time is 20 minutes. We do know that the potential difference is 2.4 volts. And we also know the current is 0.04 amperes. Now, the first thing we need to have realised here is we're working in minutes. So we need to multiply that by 60 to give us seconds. And 20 times 60, if we do it on our calculators, is going to give us an answer of 1,200 seconds. Okay, then we'll write down our equation. So E equals V times I times T. We know V is 2.4, we know I is 0.04, and we know T is 1,200. So if we now do that equation on our calculators, so 2.4 times by 0.04 times by 1,200 will give us an answer of 115.2 joules. Now in a real exam, that could be up to 3 marks because we've had to do a conversion to get there. So good marks for doing this. Well done if you got it correct. So number 2, let's again do the same. E, V, I, and T. We'll do it in that order this time. So energy transferred in 30 seconds. We don't know the energy, but we do know the time, 30 seconds. When a hairdryer has a potential difference of 230 volts, this is an important amount of potential difference because that's mains potential difference, and a current of 0.5 amperes. So we're going to write our equation again. E equals V times I times T. Put our numbers in. 230 times by 0.5 times by 30. Work it out on our calculator. So 230 times by 0.5 times by 30 will give us an answer of 3,450 joules. Okay, well done if you got both of those correct. That's absolutely fantastic. So let's have a think about what this lesson is about. It's all about power. Now, having said that, have a look at this picture. Why do you think she has this pouch? What's going into the pouch? I mean, that'll give you an idea. And why doesn't it really matter? Pause the video and just have a think about it. Well, the pouch is there to try to reduce the amount of microwaves coming off that phone. So people use those pouches occasionally because they're concerned about how many microwaves are coming off. But why doesn't it matter? Why shouldn't we worry about using pouches like this? Because the power of the mobile phone is so low. The power of a mobile phone compared to the power of a microwave is about 1,000 times less. So that means you would need 1,000 times more exposure of a mobile phone to have the same heating effect as a microwave. So, interesting to think about. And what do we mean by power? Well, we're talking about energy divided by time. It's the amount of energy in joules that's given out in a given amount of time. So 1 watt of power would be 1 joule for 1 second. 10 watts of power could be 20 joules for half a second, or 10 joules for 1 second, or 5 joules for 2 seconds. It all depends on how much energy has been transferred and for how long, because in total the energy should be the same if the power is the same. So here's our first equation of the lesson. As electrical devices are depending on the time that's needed for that energy transferred, we can compare the power of electrical devices. And we've seen this equation before, and it's used in very much the same way. Power measured in watts is equal to the energy measured in joules divided by the time that power is transferred for, that energy is transferred for, in seconds. So let's have a look at an example. Here we've got an example of a microwave having a power rating of 0.9 kilowatts. It's on for 30 minutes, and I'd like you to calculate the energy transferred. Well, just like we've been doing with the calculations that we've done at the start of this session, we've got to work out what information we have. We know we have the power being 0.9 kilowatts. Well, 0.9 kilowatts means 0.9 times 1,000, because remember kilo means 1,000, so it's 900 watts. We don't know the energy, but we do know the time. The time is 30 minutes, and every 1 minute is 60 seconds, so it's 30 times 60 seconds, which is 1,800 seconds. Everything now is in the correct units. We can't work with kilowatts and we can't work with minutes, so we have to be in watts and seconds. So we can use our equation, and we had power is energy divided by time, and if we rearrange that equation, we'll have energy is power times time. So we can do our 900 watt microwave multiplied by 1,800 seconds. We'll actually find it's a very big number. It's 1,620,000 joules, or what we could otherwise call 1.62 megajoules. Because remember, mega is 1 times 10 to the 6, which means we've moved the decimal point from here 6 spaces. 1, 2, 3, 4, 5, 6. 1.62 times 10 to the 6, or 1.62 megajoules. Okay, now it's your turn to have a go. Using the same way that we've set up this previous equation, have a go at answering this question to check you know how to use the P equals E divided by T calculation. So pause the YouTube here and have a go. Well done, ladies and gentlemen. Let's go through the answer. Well, in the same way as the one that I've done as the example, we can see we need to write down the information we have from the question. The power is already in watts because it's 5.4 watts. So that means 5.4 joules every second if we want to go back to basic ideas here, or the fact that we don't need to convert it. We don't know the energy, that's what we're still trying to find out, but we do know the time. We're told it's 50 minutes. Now 50 minutes is no good for us, we need to be working in seconds, so that's going to be 50 times 60, because remember every 1 minute has 60 seconds, which is 3,000 seconds. Now we'll use the same equation we used previously, E equals P times T. We've got 5.4 watts, so P is 5.4. We've got 3,000 seconds, so T is 3,000. And if we multiply those two together, we've got 16,200 joules, which is 16.2 kilojoules. Because remember that kilo means times 10 to the 3. So we're going to move the decimal point from here 3 places bigger. 1, 2, 3. 16.2 kilojoules. So if we've got less power, but for more time, we can still have less energy transferred. So that's our first power equation. Okay, so the next equation is P equals I times V. Now, if we know from our previous work that Q equals I times T, total charge, is equal to the current, the number of electrons, each of which got their own charge, passing a point per second, multiplied by the time that they're passing for. That means I can say that I is equal to Q divided by t, the change in charge over time. Well, if we now go to our power equation, because I can't see any time in there, and we've already said that power is energy divided by time. So let's go across to this equation over here. We've got P equals I times V. Let's substitute in this Q divided by T for every I. So that's going to be Q divided by T multiplied by V is equal to P. Now we've also learnt another equation, which is that E is equal to V times Q. Well, I can see a V times Q up here, so actually what I've said is that P equals Q times V over T is the same as E over T, which is exactly the same as what we started with. So here we've got a new equation that's using electrical power, that is P equals I times V, where P is power in watts, I is current in amperes, and V is potential difference in volts. So let's have a go at another example. Here we've got a microwave with a voltage of 240 volts and a current of 3.75 amps. And we're asked to work out the power. So in this case, we don't know P. So P is question mark. I, we know, is 3.75 amps. And V, we know, is 240 volts. So we can say that P equals I times V, PIV. We can put our numbers in, substitute them in. So 3.75 for every time we see I, and 240 for every time we see V. So 3.75 times 240 gives us 900. That's not the end of the story, is it? Because we must put our units. And our units for power are watts. Okay, time for you to have a go now. A mobile phone charger has a voltage of 240 volts and a current of 0.03 amps. Can you calculate the power for me, please? Pause the YouTube video here, have a go at this calculation, set it out in the same way, and then come back and we'll go through the answer. Well done, ladies and gentlemen. Let's have a look at the answer. We don't know power, so power becomes a question mark. We do know the current is 0.03 amps, so we're going to write that down in next to I. And we do know the potential difference, 240 volts, so we'll write that next to the V. So P equals I times V. Every time we see the I, we're going to substitute in the 0.03, and every time we see the V, we're going to substitute in the 240. And if we do that calculation, we'll find we've got 7.2 watts. So we're considering a microwave and we're considering a mobile phone. Okay, it's a charger, but let's imagine it's a mobile phone. The power difference between these two is why you don't need to put your mobile phone in a pouch that contains the microwaves. Because the power of a microwave is emitting 900 joules every second, whereas the power of this mobile phone, or mobile phone charger, is only 7.2 joules every second. So the amount of energy that's been transferred is significantly less. Okay, now we're going to put two equations together to build us a new equation for power. And the two equations we're going to use are P equals I times V and V equals I times R. And we're going to work out how to do this. And this is very much like how we would do it at A level. So we'll start with V equals I times R, Ohm's law that we've learnt so far. So V equals I times R. And we also know from the previous step that we did that P equals I times V. Now, wherever there's a V in my power equation, I'm going to put the second part of this equation. I've only got one V, so that I times R is going to go in place of that V. So I'm going to have P equals I times, and now what is in this I times R, this V equation? So P equals I times R. Well, I times I is the same as saying I squared. So we've got power equals the current squared times by the resistance. So if we now use this equation, we can see that actually current is really important in this equation in terms of the power that's being lost. So this gives us an equation for the energy being lost when a wire is being heated or when a current flows through a wire with a resistance. So we've got power in watts, we've got current in amps, remember it's a current squared, so that's I times I, and we've got resistance measured in ohms. So as we've done with the previous equations, let's have a go at having an example of this one. Here's our example. A microwave has a current of 3.75 amps with a resistance of 64 ohms. Calculate the power. So we don't know power. We'll put a question mark by it. We do know resistance, which is 64 ohms. So we'll write that in. R equals 64 ohms. And we do know the current. The current is 3.75 amps. So we'll write that in as well. So we'll write our equation. P equals I squared times R. Now for every place where there's an I, we're going to put 3.75. And for every place where there's an R, we're going to put 64. So we've got 3.75 squared multiplied by 64. And if we work this out to the end, we'll find, oh look at that, 900 watts. I think our microwave has been 900 watts the whole time through. So we've been able to work out quite a bit about our microwave because the power has always been the same. Now it's your turn to have a go. A computer has a current of 5 amps with a resistance of 20 ohms. Can you calculate the energy loss, the power loss from that computer? Pause the PowerPoint here, work your way through in the same way, and then come back and resume the PowerPoint once you've had a go. Okay, well done. So, we don't know the power. Let's put a question mark by it. But we do know the resistance, and the resistance is 20 ohms. And we know the current. The current is 5 amps. So here the power is equal to the current squared times the resistance. We write our equation every time. Everywhere where there's an I, we're going to write 5. And everywhere where there's an R, we're going to write 20. So that's 5 squared times 20. Well, that's a power loss here, or a loss due to that resistance, of 500 watts. So we'd be losing 500 joules every second if we had this resistance. Okay, so what I'm going to ask you to do is I'm going to ask you to have a go at the worksheets now that I've attached to the assignment. Make sure you show your full workings. Start with the equation practice sheet first, and then once they're completed, upload a picture for me onto the Teams channel and we'll give you some feedback. Now let's have one final go at an exam style question. So this is exactly the kind of question you would see in your exams. And it says, calculate the energy transferred by a 5-watt spotlight in 2 hours. Now you have to decide which of the different power equations you're going to use. Remember, we've learnt quite a few today. We have got power equals energy divided by time. We have got power equals current times potential difference. And we've got power equals current squared times resistance. In fact, you could have made an extra one by substituting in V instead of I. Substituting in I instead of V, and you'd end up with a different equation. I'd let you have a go at that. But which equation are you going to use? And you need to know all 3 of these equations to approach it. Pause the pause the YouTube video here, and then have a go at this question. And we'll go through the answer in a moment. Okay, well done. So let's write down what information we know and let's decide on the equation we're going to use. So we want to work out energy. we know that the power is going to be 5 watts, and we know that the time is going to be 2 hours. Well, we don't know the energy, but we do know the power and the time. Power equals energy divided by time. Let's rearrange it for energy. In fact, let's put our numbers in first. So for every P, I'm going to put 5. For every E, I don't know, so I'll keep it as an E. But for time, it's 2 hours at the moment, so we better change that. 2 times by 60 to turn it to minutes, times by 60 to turn it to seconds, because remember, we always have to work in seconds. So we have 2 times 60, which is going to give us an answer of 7,200 seconds, which we can now substitute in to our equation. Okay, that would get you your first mark. So if I was to be marking this in an exam, this is your first point because you have substituted in and you haven't rearranged. So no loss of marks in case you get your rearranging wrong. Now we're dividing by 7,200 on this side. So in order to get rid of that and leave E on its own, we're going to have to multiply by both sides. So I'm going to have 5 times 7,200 is going to be equal to my value E. Now this would potentially get you your second mark in this question because now you've rearranged it. And now it looks quite straightforward to finish. We've got 5 times 7,200, which is going to give us 36,000 joules, is equal to our energy. And that could get you another mark. In fact, it could get you 2 if you hadn't been given the unit. You might also be asked for it in kilojoules. Well, how many kilojoules are there in 36,000 joules? Well, there's in fact 36. Because each kilojoule is 1,000 joules. So 36 times 1,000 gives us 36,000. So it's 36 kilojoules. So let's just do a final recap of the lesson we've just done. We were learning about power, and we've learnt that there are numerous equations for power we can use. We have the typical power equation, which is power equals energy divided by time, remembering that time must be in seconds. There's our first one. We've also learnt that power equals current times potential difference. And remember that that comes from the fact that I is actually the change in charge divided by time. And the change in charge multiplied by the potential difference is in fact the energy. So we end up back at the same equation if we put those in. Now you don't need to know that, but you do need to understand this second equation. So power is equal to the current multiplied by the potential difference. We've also learnt that if you substitute in V equals I times R into P equals IV, or I times V, sorry, then we're going to end up with a new equation, which is power equals the current squared times by the resistance. And that means that this current squared is very important. In fact, what it means, if I was to half the current, then I would quarter the power loss. So this is why in the later lessons we're going to learn that the current is reduced when we're transmitting electricity through the national grid across the country. So remember this lesson when we come back to it in a few more videos' time. So if you have any questions, leave some comments below. If you've enjoyed this video or you found it helpful, please give it a like. And if you wish to follow on with more of these lessons, then don't forget to subscribe as well. Thanks for watching It's Not Quantum Physics.